Now then, welcome back to the channel. So, video 3. So at the end of the last video, we had put this together. I don't think I'd put the case on. It's now in its acrylic case. This has the new XR2206 chip in it, and it's working fine, as well as we can expect, given that it's probably a fake chip. So we can't adjust the symmetry, but we don't have the controls on here to do that anyway. We can control the frequency and the amplitude, and we can look at square waves, triangle waves, and sine waves. So that's okay. That's good. I've not given up on this. I think this might be useful in some circumstances, but I would like to have a bit more flexibility. So at the end of the last video, I brought this out, and this is another kit, a kit for a different signal processor, a different signal generator rather. This one using a different chip. So rather than the 2206 chip, this has in it this chip here, which is an ICL8068. So this has the main advantage of being designed in this millennium rather than the last one. So this chip, I think, was released in 2001, whereas the XR2206 was released in 1972. So I think without further ado, the thing to do is get this assembled and soldered together, and then we can have a look at what it produces on the oscilloscope, see if it works, and go from there. So my soldering iron is heated up, so I will get on with that now. So just before I start actually soldering this all together, it's worth pointing out that this kit came with no instructions at all. So there are no indication from this which part goes where on the board, which potentiometers go into which different locations. There are two different values of potentiometer that go in those 4 positions. I think the 2 trim pots that go in are the same. I also can't find a full schematic for this board either. So a lot of it is best guesses. There is an excellent Instructables article that looks at a very similar board to this, but it's not identical. So I'm hoping that most of it is the same. It looks like the only difference is where we are looking at here an LED, which I'm assuming just indicates that the power is on, but also this R17, which I think is going to be the current limiting resistor for the LED. I can't see that on the traces, certainly not on either side. Oh yeah, we could just about see, if you get the light correct, that the resistor is connected to the LED. So I think that is the current limiting resistor. So I'm hoping that all of the rest of the parts will be the same, and when I get to identifying what R17 is, then that should be the last leftover component. So I'll get on and start putting it together. Right, so that's all the soldering done. I think it wasn't too bad. You might laugh at my soldering efforts, and if you've got any tips, feel free to put them in the comments. More than happy to take constructive advice. Since I recorded that, I've done a couple of things. I have cleaned up a couple of the joints, just reflowed them. I have actually remembered to solder the pins of this socket, which I forgot while I was actually recording. There we go. And I've connected some jump leads to the outputs of the board. All that remains is to put the chips in. Except I think we'll do a couple of checks before then that we just to make sure everything's fine before we go ahead and put all of the chips in. So power supply is at 12.24 volts. That's fine. That's pretty much what we would want. The LEDs are the right way around. That's always a result, isn't it? So the other thing, you can't see it because of the LED, but first chip in here after the power socket is 78L09. So that's a 9 volt voltage regulator. So if we have a look at the back of the board, we can check the input power supply. It had it there for a second, it's 12.24 volts. If we look at the output from the voltage regulator, it's 9.13 volts, exactly what we expect. So that should go straight over to this socket here. So if I come in again and take the ground off the barrel of the DC connector, this is the voltage in for this chip. 9.13 volts. This will be the voltage out, which at the moment isn't anything particular. So once we put that chip in, that should be generating, I think, -7 volts, -7 to -9 volts. So let's quickly pop that in. That went in quite nicely. I think I've got all the pins in correctly. They look right to me. So again, input voltage on pin 8 is 9.13 volts, output voltage -7.8, so -8 volts. And they provide the positive and negative supply voltages to the op amps, which is the TL082, I think. So if I disconnect the power, I can pop that chip in to its socket, making sure it's the right way around. So we know its voltages will be okay, so it should work fine. And the voltages to the actual function generator chip should be fine as well. Okay. So we can power that up, and we can take a look using an oscilloscope as to what this thing's actually producing. So we'll start with the sine wave. If it works. Okay, let's plug that in, get some power to the oscilloscope, put that boot up, maybe zoom in a tiny bit. There we go. So we have nothing on there, but that is just what we'd expect because the amplitude's turned right down. Turn the amplitude up, and the frequency up, and we're seeing nothing. Absolutely nothing. That should. Okay. Well, if that's not doing anything, let's try the square wave. So the square wave bypasses most of the control beyond. Let's get that a bit. Oh, there we go. I knew it wasn't that bad. At the frequency down, and we do have a square wave. Okay, there we go. Well, that's a relief. Not quite sure why that wasn't showing up. So the square wave isn't affected by the amplitude control or by the DC offset control, or it is by the frequency and by the duty cycle. So that's all looking all right. I quite like that. That's looking good. So let's just try the sine wave again and see whether we're seeing anything there. Oh, we are. Okay, so we should be getting a nice sine wave out of this, and we're not. I think if we get the duty cycle in the middle, that should be a bit more symmetrical. Oh, this is looking good. Oh, we can't control this with the DC offset at the moment because the oscilloscope is AC coupled. But there we go. We can change the DC offset as well. So that's all working fine. Quickly check the triangle wave. And then that's looking brilliant. Exactly what we need. We can use the duty cycle control on the triangle wave to turn it into a sawtooth. I don't like the way it's affecting the frequency, the way that it is, but okay, that's fine. That's absolutely fine. Let's get this up to about 2.5 kilohertz and see where we are. Oh, right. Okay. So a bit of investigating with that. I'll quickly go back to the sine wave. So this chip, unlike the XR2206, has separate output lines for the triangle wave and the sine wave, as well as the square wave. So on the 2206, there was effectively a jumper that you could put in. If that was connected, you'd produce a sine wave. If it wasn't, it'd produce a triangle wave. But this can produce both. So this is actually selecting which of the output pins from the chip is connected to the input pin on the op amp. So if I should now be able to make this sine wave look a little bit nicer. Okay, so let's drop the frequency a little bit so we can see the shape. It looks a little bit pointy at the top and a little bit offset at the bottom. So if we get, right, that's a bit more symmetrical. That's good. There we go. There we are. So these two potentiometers here affect the shape of the sine wave. So that's now got us to a stage where we can use this, I think, effectively. We can also skew the shape and the frequency of the sine wave using the duty control. Let's just go back to the triangle wave. So one of the reasons I like this more than the XR2206 is because you can generate sawtooth waves. What you can't do, I don't think, oh, actually maybe you can, is you can generate actual proper sawtooths and also reverse sawtooths. And I like that. I think that's good. So I think this is going to be good enough to actually start doing some work with a couple of projects and we'll talk about those in a second. So the next step up from this effectively would be to go, instead of using one of these chips to generate the different waveforms that we're interested in, it would be to go fully digital, go to direct digital synthesis, use something like a microcontroller to generate any arbitrary waveform that we wanted, not just sine, triangle, square wave, sawtooth, but any much more complex thing, and to generate things like the types of waves which are produced by summing together harmonic series of frequencies. So that kind of thing we can do with the microcontroller. Whether it's the best use of the power that a microcontroller needs, I think that I'm not entirely sure. So I'll be having a look at that. But in the meantime, this is going to be good enough to actually do what I need next. So the next video, we'll actually be looking at a kit that I put together a few months ago, quite a while ago actually, which doesn't work. It's a guitar effects pedal, which is mostly working, but the signal's not coming through quite as strongly as it should do. Now it's quite difficult to generate or to put through stuff with the guitar directly and monitor it and see what the actual effects of the output of that pedal are on that guitar signal. So using a function generator lets us put a pure waveform in and see what the output's like. So we can actually understand better exactly what that pedal is doing. So that's what I'm going to do next. So if you like this video, by all means click like and subscribe if you want. Otherwise I will see you in the next one and we'll actually get something more practical done.